I work at MIT in Cambridge, Massachusetts. I am not in Cambridge, Massachusetts right now. I am in Orlando, where I grew up. I grew up in Florida, and behind me is a lot of art supplies in various cases because my mom runs a nonprofit arts organization that promotes the work of professional women artists and also advocates and provides tuition-free art education for youth and for adults. So her path definitely influenced mine, and it is part of why I am who I am. And so I will talk a little bit about that as I go on. In terms of questions, please feel free to drop any questions into the chat as they come up. I am more than happy to answer any questions. And yeah, so let me just start with telling you a little bit about myself and how I got to where I am. When I was in high school, I actually wanted to be an English major. I really wanted to study English, literature, poetry, you name it. And it was like my strongest subject. But I was also interested in math, interested in science a little bit. My mom is an architect, and so I always sort of grew up with that like technical but artistic imagination in the background. So I was really interested in that sort of like technical thinking. And so I was like, maybe engineering, I don't know. I liked dreaming up ideas for things, like drawing really complicated maps and designs. So I like to understand how things worked. And so when I got into my more advanced math classes in high school, like calculus, for example, I realized, oh, wow, this is really cool. I really like how this all fits together, how there's like this way to solve problems that's built on every single kind of math I've learned about before. This is amazing. Where can I get more of this? And so that's where more of my interest in STEM started to come out. And I settled into astronomy because I got interested in astronomy through, I think I was watching like Nova or something on PBS, like one of these like space shows. And I was like, this is amazing, like black holes and dark matter. And nobody knows the answer to some of these questions. Like there's still so much to do. I think sometimes when you're sitting in science class or history class, it feels like everything's already been discovered, everything's already been figured out. And so to find a field presented in this way, like there's still mystery, there's still wonder out there in the night sky, said, I want that. Let's go do that. So that was what motivated me to go to MIT, was to get this technical background to understand how everything worked. So while I was at MIT, I studied physics because I wanted to really just understand how everything underneath everything else worked. And so that's what the picture on the top left is. That's me working 2 kilometers underground in a lab that was built into an active mine. And what I'm doing there is I'm holding this tray that is the data acquisition unit. Basically, it records the electrical impulses from a dark matter detector that was off outside the picture. It was just like this gigantic, like 2-ton stainless steel detector that is trying to measure the tiny little flashes of light from when a dark matter particle bumps into a molecule of liquid argon. So that's what we were trying to measure. So I was doing this as an undergrad in college, and I couldn't believe it. It was so much fun. So I was helping basically plug in all of the cables and make sure that this humongous complex experiment worked before getting the party started and taking real data. I also learned that I really liked talking about science and finding ways to explain science that are out of the box and interesting. And so over on the right, you can see I am letting a bunch of sparks fly into the air. This was for a physics demo that's on YouTube. It's the MIT K-12 video series. One of my friends was actually making these videos, and she asked me to be the host for this one, where we're pushing a bunch of electric current through a really thin wire, and it's too much current, so the wire explodes, and it was awesome. So I realized, like, hey, this is really fun. I like this a lot. And the other thing I did was I majored in physics, but I minored in writing because I loved English and I wanted to keep that part of me and not give up on it. So I ended up writing skits and radio plays, and MIT has its own radio station. So I said, hey, let's put a radio show together that is a drama about space. And so I learned how to be a radio DJ, and I did that while I was a student and then also while I was working as a member of staff at MIT. So if you're worried about having to choose either science or art or between two interests or multiple interests that you have right now as a high schooler, I would like to offer myself as an example of you don't necessarily have to choose. You can find different ways to make your interests part of what your college career is. And you can take that also to your work career as well. So what I do now is I research exoplanets and I continue to find ways to weave together art and science. So on the left, this is a picture of me standing in front of Tess on the Falcon 9 rocket before it launched. So Tess is in this little tiny fairing up here, and Tess maybe occupies like this much of it. It's like this teeny tiny satellite. It's maybe like smaller than a refrigerator. And we got to go to the launch pad. This was back in 2018, a couple days before it launched. And I was like, I need a picture. This is awesome. So it was really meaningful because, as I'll talk about in a minute, I worked on the cameras for this telescope. So to be able to see it on the rocket right before it was going to go up, I was like, this is unreal. So I highly recommend working in aerospace and like specifically on NASA missions if you want to have this crazy feeling. So the other thing I do is I try to continue with art and continue with communicating things to the public in a way that helps you understand science, not just like the equations and what's going on in the background, but also like a sort of in your heart feeling of understanding. So my mom is an artist, as I mentioned. She's really interested in how light, like our relationship with light. And so I learned a lot about photography while I was a college student. And so I worked with her on a photo series. One of the pictures is here. She took a portrait of me using long exposure photography and colored lights. And actually you can see one behind me here in my office. This is another one of her works. So helping my mom, helping other artists connect with more technical types of media. And then also really mushing the two together. These two pictures are on the right are from a concert I put together last year called Songs from Extrasolar Spaces. So Tess had a conference to celebrate our first year of science and share that with our astronomy community. And I wanted to find a way to share that feeling of accomplishment. And oh, I think I disconnected for a little bit. Am I back? Okay. So I wanted to find a way to share this feeling of accomplishment and discovery that we had with all of these scientific research talks with the public. So I worked with a composer at MIT, Elena Ruhr, who wrote two new pieces of vocal music. And I wrote the lyrics for one of them. I put together lyrics based on all of the titles of the scientific papers. And I worked with this vocal ensemble, the Lorelei Ensemble. The director is in this top picture. And we put together this concert for the public that conveyed artistically the feeling of discovery of exoplanets. So that is the kind of thing that I want to keep doing for the rest of my life. So if you want to see, and I'm sort of making it up as I go along and trying to just figure out how this works. So I think that is definitely a good sign that nobody has said, no, you can't do this yet. So if this is something you're interested in or whatever your interests are, you can do it too. So this is sort of all a little bit about me, but now let's dive into more of the science. So thinking creatively about these questions of discovery, and planets around other stars. We think, what's like one of the first questions that comes to mind? Are we alone? That's a biggie. And I think that often comes like just looking out at the night sky in your backyard. Are we alone? And this is sort of a philosophical question, but this is also a scientific question. And I recently had a student ask me, this seems like a childish question, but are we alone? And I said, no, that's a real question. This is a thing that astronomers spend years and years of their lives thinking about. So this is one of the things that frames what I work on. And the other question is, how unique is Earth? And this is a picture of Earth taken from one of the Apollo missions from space. And just looking at Earth, we can see it's blue and brown and has little bits of white. And that indicates we have water, we have land, we're not covered in lava, and we have this thin, precious atmosphere. And this is all balanced together in such a way that life has been able to evolve. And now we're here having this Zoom call as humans. So, how unique is a planet like Earth, able to sustain an atmosphere and water and able to have the ingredients needed for life? So, these are the questions that motivate a lot of exoplanet research and sort of connect exoplanet science to the real world. Often people ask, why is this important? Why do you care? And this is why I care, because I think everybody has this question. So we should try and find an answer to it. So I mentioned TESS. I showed you the rocket. This is what TESS looks like. It is, I think I mentioned it's the size of a refrigerator or so. It has 4 wide angle cameras on it that are set up inside the spacecraft to stack up on top of each other in terms of their field of view. So each field of view covers 24 by 24 degrees on the sky. And they stack up on top of each other to make this long strip of sky called a sector. So this is 24 by 96 degrees on the sky. Whoops. And we're going to have an astronomy moment where if you go like this and stretch your arm out on this, and then if you do this in your backyard, this amount of sky between your thumb and your pinky finger is about 25 degrees. So that gives you an idea of just how much sky TESS's cameras cover. One constellation, like Orion, for example, can fit into a TESS camera. So we're covering huge amounts of sky. And we're doing that because we're trying to map the entire sky looking for exoplanets. So this is what the 4 cameras look like. You can see that they're kind of angled differently, and that's so that we can get that nice stacked up sector field of view. These black cones of shame, they're called light shields. And what they do is they keep light from the moon or reflected light from the Earth from getting into the cameras and contaminating them. You can see that TESS has a little green coating on the lens of the camera, and that's because TESS is looking at light that is in the optical wavelength, so light that we can see, but light that is from a little bit further down the color spectrum, so from somewhere in the greens all the way down into the reds, almost into the infrareds. So that filter is there to cut out all of the greenish, bluish light that's that is in those wavelengths, yes. And so here you can see a couple of people testing the solar panels for TESS. This is when it was getting assembled down at NASA Goddard. The part that I worked on was measuring how well focused the cameras are. There's no moving parts inside of the cameras, so you have the camera assembly here and the lens is here. If you've ever taken apart a digital camera, like a DSLR, or seen them on TV, you can see there's like the body of the camera and like the big long stack of lenses. And the TESS cameras are kind of the same. And so we had to understand the distance between the sensors and the lenses and make sure that that distance was exactly correct such that the stars would show up in focus and not blurry. And it turns out that we did a good job because everything came out okay. In the testing in the lab, what we could do is what we did every time we turned the cameras on to make sure that they were working, we would just take a picture of them just in the lab. And so this is a picture that I took with 4 of my colleagues because they were there and I said, hey, let's take a picture. And you can see that the cameras can operate at room temperature. They operate best when they're cold. That's what makes these little lines go away. And the camera shutter stays open for 2 seconds. So I moved, so I'm blurry. But our exposure time is 2 seconds. So you can see that these two are a little bit more in focus and we're a little bit more out of focus because we moved. But what I like about this picture is that each one of the people in this shot is a person who now works with test data. Deanna is an exoplanets expert. Jen is a telescope expert, and Elizabeth is an expert on stars, and they all use test data. So this is, I think, TESS summed up in a picture. So I mentioned a little bit so now that we've talked about the cameras and what they do, what is TESS doing? So it stares at each one of these sectors for 2 orbits. It orbits the Earth, and its orbit takes about 2 weeks. So while it's orbiting the Earth, it's staring at each one of these sectors of sky for about 2 orbits or maybe 27 days each. And then it moves to the next one and then moves to the next one. So while it's in each of these sectors, it's taking an image every 30 minutes. So we have this like time-lapse movie of that part of the sky for almost a month. And then in these bottom and top portions where all of the sectors overlap, they're getting observed the entire time TESS is looking at that hemisphere. So you get almost a year of data in these sectors or in these areas. And that's really exciting because you have a year-long time lapse basically. So you can study the stars in those areas. Oh, so this is the slide where I mentioned being able to see Orion. So that is a fun project for you later tonight. So these are what the TESS images actually look like. Each of the 4 cameras is divided up into 4 smaller CCDs. Basically, they're just detectors. CCD stands for charge coupled device, but it's like a totally useless acronym. It just means camera sensors. So this is one camera, this is another camera, another. And you can see part of the Milky Way that we're observing in that sector. You can also see this is the Large Magellanic Cloud here in this camera. So these are beautiful images just on their own, and these are all public images. Test data is all online. So if this is firing your creative juices, you can download these. And so TESS, that was just one sector, but TESS mapped almost all of the southern hemisphere and most of the northern hemisphere, almost 70% of the night sky in 2 years. And so you can see we got most of the galactic plane in there. So if I zoom in on one of these images, the stars look like little blobs. And this is because we're not necessarily going for aesthetics. It's nice that the pictures look this way, but what we're trying to do is measure all of the light coming from that star. And so this star, which is super duper bright, is it was so bright that basically you can think of each pixel as a bucket. And so a bunch of light fell into that bucket and then flowed into the pixels next to it. And so we count up all of these pixels and we get a pretty good idea of how much light is coming from that star. And then we do that over time and measure this much brightness in this frame, this much brightness in this frame, this much brightness in this frame. And we see how it changes, and we can then use that to understand what's going on with this star. Whoops, I went way too fast. Come on. No. 1 second. Here we go. All right, so what's going on with the star? So for a star that has a planet around it, as the planet crosses in front of the star in its orbit, from our point of view, the planet blocks out a tiny amount of light from that star, which creates a dip in its brightness here, this light curve. And so I'm going to start the animation again. This is a bonus animation. I did not know that was there. So a small planet has a small dip, and a large planet has a large dip. So we're looking for periodic dips in the star's brightness. And this is in the wrong place, but I'll talk about it anyway. So one of the things that you can learn from tests is based on the ratio of based on the amount of light that's blocked out, you can find out how big the planet is, and then how often these little blips happen as the planet goes in front of the star. You can figure out how close it is to its host star. And based on the brightness of the star, you can figure out, okay, how far out does this planet have to be in the habitable zone of that star? And habitable zone has a few different definitions, but the sort of general agreement is habitable zone means that the planet is in a range where it could sustain liquid water on its surface. So I mentioned watching the light change over time. So this is a real light curve with real data. And you can see that there's a lot of bouncing up and down. The data's kind of messy, but you can definitely see a dip when the planet transits in front of the star. So here we go, planet going in front of the star, boom. Here's the dip from the transit. And so we do this for thousands of stars across the night sky. And the place where coding comes in is we use machine learning and other tools to help us recognize transits coming from planets versus just stellar noise, like the star just flaring or doing its own thing, versus something coming from the instrument or or another type of like two stars going around each other, for example. So we use a lot of data analysis tools to help us narrow down the millions of stars that we observe in the night sky to a manageable few hundred that we can look at every month with a group of people. And so I thought I would show you what that looks like. We have reports like this one, where you can see this is our light curve, and this is our planet transiting. We can see the little blips in the light curve. And then there's this big gap here because I mentioned TESS orbits. TESS has 2 orbits per sector. So this is when TESS like turned around, beamed a bunch of data down to Earth, and then turned back on to keep observing. So we have these. And then if I stack all of the transits on top of each other, that makes my signal stronger. It gives me a higher signal to noise ratio. So that's where I can see, oh, hey, this looks really nice. This looks like it might be a planet transit. And this is like zoomed in what that looks like. And I'm just going to ignore all of these things. I won't explain them to you, but they basically help us decide, like, is this a planet or is this something else? And so this one we labeled planet candidate, and then telescopes all over the world can go look at it and confirm, yes, this is a planet, and let's go find out more about it. This, however, is not a planet. Let's just take a look at the light curve and find out why. So we can see that the transits that it's highlighting are nice and deep. They're happening really frequently. The orbital period, or how often this is happening, is every 3 days or so. So the year on this planet is 3 days long. So your birthday would happen every 3 days. And we see that this is a much deeper transit relatively. The planet radius is calculated and reported here down at the bottom. And it's saying that this is 27 times the size of Earth. Now, Jupiter is only 11 times the size of Earth. So this thing is over 2 times as big as Jupiter. So that's already making us suspicious. But then sort of the death knell for this planet, or for this candidate, is this guy. So in between the deep transits, there's another little baby transit. And this is an eclipsing binary, and I'll tell you why. When you have 2 stars orbiting each other, when the small planet transits behind the big planet, you get a little dip in the brightness of the star. And then when the big star blocks out the small star, you get this deeper transit. So this mimics planets, exoplanets, but it's a tricky red herring. All right, So take a look at this and maybe think to yourself about what you think this might be. Just take a minute to study this one. Also, Julia, you mentioned a really good question, a really good observation about the test image. Yes, those images are black and white because all we're doing in each pixel is counting up how much light fell into the pixel. And so that ends up looking like black and white because we're just assigning color scale when we look at the images on the computer by how much light is in each pixel. So no light is totally black. As much light as the pixel can hold, totally white. Everything in between is gray. The way that color photography works with digital is a little bit different. What it's doing is it's splitting the light into channels. And so you're collecting all of your red light, all of your green light, all of your blue light. This is like I'm like a little bit hazy on how color digital works, but I think that's the gist of it. We use, the cameras are kind of like normal sort of binoculars, like they let in all of the light between about 600 nanometers and 1100 nanometers. So a lot of optical light. And in order to get like just one color, just one wavelength, you have to have a very strict filter on your lenses. But yes, okay, I am glad that made sense. So coming back to this guy, what do people think this is? Okay, Isabel, yes, you have good reasoning. I am with you that this has a small radius. It's not as offensive as the other one. And yeah, this pattern of dipping is different from the binary, but it's still weird. Like, what is this flare happening here? Why is it going dim and then bright? And so when astronomers first saw these systems, they realized, oh, hey, this is stellar variability. This is the star having pulsations in it because of how it's rotating, how it's behaving, where it gets dark and then gets brighter. And so stellar behavior, because stars aren't well behaved most of the time, is also something that can look like a planet candidate. But at first, you might think, oh, hey, so this I think really draws home for me, at least, like we're interpreting the behavior of gigantic stars and planets based on how a bunch of little dots are behaving on a piece of paper. And I just think that's so cool that we use this to imagine things that are so distant and so different from us. So here's the last one that I'll show. This is, how many sectors of data is this? This is 1, 2, 3, 4. I think this is at least, I think this is from the whole year of observing the Southern Hemisphere. We have 13 sectors of data here. There's a lot of noise in this light curve. And then you can see this thin red line. This is the model for the fitting the transit. So what do you guys think? Planet, not a planet, nothing? I agree, it is pretty funky. This is the zoomed in one, if that helps at all. If this is a planet, its temperature is 328 Kelvin, and it's only 2.7 times the size of Earth. So I'll let you guys know that this is a planet candidate. This is part of a system called TOI 700, and this is actually the first habitable zone planet discovered by TESS, Earth-like habitable zone planet discovered by TESS. So it's small, and so now this is a really exciting candidate to go look at with other kinds of telescopes. But we really needed to look at it carefully and say, okay, I'm gonna take a chance on this one. I think this might be a planet. So if this was really fun for you, there is a whole website dedicated to giving the public test data to identify transits. So that's planethunters.org, and it's run by this really cool grad student, Nora Eisner. So I definitely recommend checking that out. So now I'll zoom way out and give you the big picture. this series of graphics, I worked with a high school intern to put together this idea for visualizing Grecky Basile. So previous to TESS, we had looked in really focused areas of the sky for exoplanets. This big patch here was observed by the Kepler mission before TESS. And then when Kepler broke down and switched over to K2, it observed here along the ecliptic. So this is the before, and then this is with TESS. So these are all of the exoplanets that TESS has discovered that are in our TESS Objects of Interest catalog. So almost we're getting to the point where we're contributing a huge number of planet candidates to the exoplanet community. So altogether, we have thousands of exoplanets that we have identified across the night sky. And so this gives us an answer to that question that we posed in the beginning. Are we alone? And now knowing that there are all of these exoplanets out there, there's likely even more that we're not detecting. So I would say that the answer for now is not really. But yeah, these are great questions. I saw one from Srikanth about podcasts. I definitely recommend Exocast. It's a podcast all about exoplanets that is created by 3 exoplanet astronomers, and I work with one. So I'm almost obligated at this point to recommend this podcast. But yeah, Ji-yoon, thank you for hosting me, and thank you all for your attention. This has been great.
Thank you so much. So if anyone has specific questions, yeah, let's definitely get them out there. I, for one, have a specific question in mind, which is, what do you think has been the biggest challenge, going into the whole astronomy industry and field?
Oh yeah, that's a good question. So I think the biggest challenge was finding ways to sort of make sure that I felt that I belonged. And so I definitely struggle with imposter syndrome. I'm sure you guys have talked about imposter syndrome. And I think like being someone who expects a lot of themselves means that you can always find ways you're never going to stop growing for sure. But I really wanted to make sure when I started on TESS that I had people who I trusted in my team who I could go to and say, hey, how am I doing on this? Like, what can I do better? And that they would give me good advice instead of tearing me down or not telling me what I needed to hear. And also people who would speak for me. I don't know if you guys have talked at all about sort of bystander intervention or any of that, but I am in a lot of meetings as part of my work. And sometimes I'll have an idea or I'll need to change the subject to something else in a meeting that I'm leading. And it's really helpful to have people in the room who are on the same wavelength as me, who, if I say something and it gets ignored or somebody else repeats it, they can pop up and say, oh, Natalia just made a really good comment about that. Natalia, why don't you say something about that? So I think that was like something really amazing that I was able to find in my team, people who had my back and who could support me.
Thank you. I think we have a lot of good questions in the chat too.
Cool. I can.
So,
do you want to call them out?
I can if you want to. Did anything surprise you about working with NASA?
I was surprised at how friendly everyone was. Everyone at NASA that I have worked with, at least, is so nice, and everyone is just genuinely excited and engaged in the mission and the data and the results. And so I was really blown away by how close-knit and friendly the relationship was between our team at MIT and the NASA team and all of the teams. It just like made working in a collaboration so much better. Like if you are sort of think about the things that you like and dislike about group projects, and TESS is essentially like a giant 3-year group project at this point.
That's awesome. So next one is, what's the most exciting project you have worked on?
I think one of the most exciting things that I've worked on has been definitely testing the cameras and just having that experience of working on something that's now orbiting the Earth. Like that was amazing to have that impact on, and just like know that. I'm just like, oh, I took data with that, and like I sat up all night and analyzed it. Super cool.
And as a woman in STEM, what challenges have you faced and how did you overcome them?
Yeah, great question. The the gals in STEM life is a struggle. But I think that what's amazing about astronomy is that I have found a group of, in general, people who I really trust and who I draw support from, but in particular, women and women mentors and just like informal friends. Um, Women who I work with, and I was really lucky that we had so many. Like I showed you the picture of like the 4 of us, and I was just so lucky that there were 4 women postdocs. So postdocs is what you do after grad school, who were doing research on tests right at the beginning, who I could talk to and bond with and go to lunch with. And whenever I was like stressed out about a presentation, just like, oh, I don't know if I'm ready, they'd be like, no, it's fine. Or if I said, oh, I have to write this tricky email, how do I do this in a way that works, they'd look over my shoulder and help me. So I think, especially when you are the only woman in the room, it's really good to have a support system of people who you know have your back. And often in meetings, I was the only woman in the room, and I was the only woman of color in the room. And I think just repeating to myself and knowing from the interactions I had with my friends and my other colleagues that I belong here. I have as much a right to be here as anybody else. This is my space. I'm excited. Let's do some science. That really helps, but having that support system was essential.
Thank you so much. And I know a lot of people here can definitely take away a lot from that, since we are EmpowHer. But whoop whoop. And the next one is, how did you figure out what area of engineering you wanted to go into? Did you try a lot of different things, or were you able to figure it out right away?
Oh, I still haven't figured it out. I did try a lot of things. I like to think of it as like I have this toolbox and I'm just like putting more tools in. So in college, I took a coding class. Like you guys are so lucky, like you're learning how to code right now. But I took a coding class my second year of college. I wanted to understand how circuits worked, so I took a circuits class. And then I took a photography workshop because I wanted to understand how film photography worked. And that ended up being really useful for understanding how a telescope camera works. So I did try to explore and try things out. And I also had friends who were in these other fields. So I had friends who were mechanical engineers and chemical engineers and biological engineers, and learned so much from just talking to them and asking them how they like their classes and their projects.
Awesome. And who were your role models when you were just getting started?
Oh, my mom. Yeah, my mom is not from the US, and she did college right after she came to the United States. And it was her first time like speaking English. She'd studied English. And so she says, like, I would study with my textbooks and then a dictionary. And so, and just her passion for architecture and now for her organization, even though I'm doing something totally different, just like her work ethic has always been my inspiration.
That's sweet. And was there anything you did in high school that related to aerospace?
A little bit. I had a teacher, I took AP Environmental Science. I don't know if they still offer that. Okay, you're nodding. And we did this egg drop competition and Orlando, so it was at Universal Studios. And like the theme was Spider-Man somehow. I don't know, it was strange. But yeah, that was like my first and only, that was like one of the sort of big aerospace experiences that stood out to me, was like making this like little mission to land on to land our eggs safely. I think our team made the theme Spider-Man. I don't think the overarching theme was Spider-Man.
Amazing. And another question is, what innovations or discoveries would you hope to see in the astronomy field in the future?
That's a great question. I think I would really love to see like more and bigger telescopes. I think both space telescopes and telescopes here on Earth. When you look at the big picture of astronomy, it's what wavelengths have we looked at and what parts of the sky have we looked at. So being able to fill in more of the gaps of, did we look with this wavelength at this part of the sky? No, we haven't. What if there's something interesting there? Like, what if there's something we haven't studied? So that I think is what I'm interested in. I also think it's really cool that there's like projects to try and figure out like propulsion that make things go really fast. And like I have had no time to like research that, but I think that that is really cool. Like trying to get humans to travel more quickly through space.
What is your day-to-day life as an astronomer?
It's a lot of communication. It's a lot of email, actually. It's a lot of writing email. It is a lot of talking to colleagues, leading meetings, being in meetings, collaborating on things, making sure, okay, we have this new set of data. Are there any bugs in it? When can we get it processed? Is it done processing? Okay, when can we get it vetted? Okay, now that we have it vetted, we need to talk to the people about candidates to release. Oh, hey, we heard about this weird candidate. They came back and we're not so sure about it. Okay, let's look at it. Or like, hey, what if we like analyze this data using a totally different model? Like, would that be cool? So it's a lot of talking and communicating with each other. And then you go into your corner and work. But a lot of it is day to day, yeah, talking to people and making sure that you're all on the same page and moving forward together.
Awesome. Sounds so collaborative.
Yeah, I like it.
Yeah, definitely. And this is a great question. So, what is one piece of advice you would give to a girl interested in STEM and close to applying for post-secondary education?
Good luck. I would say at this point in your life, be really open. And when opportunities come up and they are exciting to you, say yes. And don't be afraid to seek them out. The way that I got my first research position when I was in college was I wandered around the astronomy department looking at the research posters on the wall until somebody asked me if I was lost. And then I said, no, I'm actually looking for a research position. And he said, oh, we just wrapped up our group meeting and I know someone who could talk to you. So like seeking out opportunities in sort of unusual ways is, I think, a valid option. But yeah, I think being open, and especially if you have a lot of interests, looking at the options in front of you for ways to fill your toolbox or ways to sort of get, even if you don't have like a 15-year plan or something, because I did not start college thinking I want to work on test mission, NASA missions. I started college being like, I want to work on astronomy stuff, maybe. So making decisions that help you get that help keep your options open until you find something that you really want to do.
Awesome. And Avi just asked what kind of cameras you use for astronomy when it comes to determining planets and wavelengths.
So TESS is these sort of wide angle small cameras, and we look in the optical, but there's also cameras that look in the infrared for smaller, redder stars. There are all sorts of different cameras. Like the Kepler camera design was totally different. It had dozens of these little tiny detectors, and it wouldn't save the whole image. It would only take like a few pixels around each star. So it would just take these little postage stamps. And or there's other telescopes like the Chandra X-ray Observatory that it has like an X-ray detector at one end. There's like this really long tube, and then the X-rays come in the other end, and then all of this tube is used to sort of like focus the X-rays. And so just like the way that telescopes are designed is wild. I love it.
That is crazy. So, okay, well, with that, I want to be respectful of everyone's time because technically we were supposed to start at 6, which I again want to apologize for. But Natalia, thank you so much. I loved hearing you talk about your experiences and about tests. I know for me specifically, like I love art as well as science, so it's just refreshing to hear someone who also has the same interests and is doing an amazing job and an awesome career. So,
Thank you.
yeah, thank you so, so much. And thank you everybody for coming. I will email the recording to everyone who registered. So I hope you all have a wonderful evening.
Yeah, it was wonderful to digitally meet all of you. Take care. Good luck. Bye, all.